Okay. Now, aldehydes and ketones are a double bonded oxygen and carbon, as opposed to alcohols, which is a single bonded oxygen and carbon. Now, there are two variations on this. Just like with alcohols, we had an OH, and then we had a ether, which was an a COC. Now, between the two, aldehydes are going to be more reactive. In fact, they're very reactive. We'll see in a little while here. Okay, this is a couple models of them. Okay, naming these now. You've got, for aldehydes, think of aldehydes as aldehydes, okay? And it's going to be in the, for the functional group. And I want to caution everyone, and okay, I want you to make sure when you do an OL or an AL, make sure it's an A or an O. So we need, and so the this is going to be the functional group. So when you name your aldehyde, make sure that the longest chain backbone contains the functional group for the aldehyde. For example, here the functional group is not that. That does not contain the aldehyde. And when I say contain it, that means a highlighted marker must go through the aldehyde. Everything else is the same. It's going to be like if we were naming this guy here, that would be the backbone, which is 1, 2, 3, 4. So it's going to be a butanal. And there's a branch on carbon 3s, a methyl branch. So say 3-methyl butanal. So it's very consistent with what we've been doing with alcohols. These are some common aldehydes, particularly this one here. That's what happens to ethanol in your liver once it's oxidized to ethanol. And then from ethanol, it's oxidized onto acetic acid, which you excrete.
Pardon me, the slide above, why did you count only 4 carbons, not the 5, the longest chain?
On which one?
Ethylbutanol. For the 2-ethylbutanol, I see that there's 5 carbons in a row, but you counted from, you went upwards towards the carbon with a double bond of oxygen.
That's right, because you have to have the aldehyde functional group in the backbone.
Okay. Oh, okay.
And that was my point of with the red line, is it's not that, because that does not contain the aldehyde group.
Okay. Perfect. Thank you.
And that applies to alcohols as well. And that also applies to well, anything organic wise, except for alkanes, because alkanes really don't have a functional group. Does that make sense?
Yes, thank you.
Okay, ketones. Okay, one last thing on aldehydes. Aldehydes have to be at the end. No exceptions. by definition, aldehydes are at the end of the backbone. Hence, you cannot have circular or cyclic aldehydes unless the aldehyde is a branch. Ketones are in the middle, no exceptions. And cyclic, and the only carbonyl that's part of the cyclic, ring, has to be a ketone. It cannot be an aldehyde unless you had something like this. So the aldehyde can be a branch, but not part of the ring. Okay, so and this, of course, is synthesized from an alcohol, a secondary alcohol. Same with this. Let's see, we got 5. Okay, and a ketone, the functional group name is got an ONE there.
Sorry, Professor, I have a question.
Sure.
For an aldehyde, so can an aldehyde be in a ring formation or a cyclo formation? And if so, what does that look like?
Say again.
What does an aldehyde cyclo formation look like?
An aldehyde synthesis? Are you asking?
Because for the ketone, we have the ring formation for it, but is there a ring formation for the aldehyde?
In terms of what?
What it looks like because
Mean to synthesize it?
Yeah, like can we, like, if we were to draw a structure, would we have a naming, like, because for the ketone it starts at 1 still for the ring structure, but I thought for aldehydes it was whenever it starts at 1 it's an aldehyde.
Yeah, so okay, I think I understand your question. The functional group always is 1 with aldehydes. So carbon number 1 is where the aldehyde is. Was that your question?
Yeah, thank you.
Okay, yeah, unless it's a double aldehyde, and then you just name one of them as 1. Doesn't matter which one. Now with a ketone, you don't start with the functional group. You've got to start on one end or the other of the non-cyclic ketone. If it's cyclic, you'd start on the carbonyl group, the C double bonded O for number 1 carbon. Okay, acetone is probably the most common ketone you're going to run into, particularly in our class. Acetone is used as a solvent frequently. If you've ever used fiberglass resin, frequently they'll use acetone as a solvent for the resin itself. The official name is propanone, common name is acetone. Now, um, this is a much stronger intermolecular force oxygen than the double bonded oxygen. So it's moderately polar, Nothing compared to the OH in a alcohol. It's probably similar to an ether in terms of polarity. Now, if we looked at the good old graph again, we've got there'd be three little lines up here for the alcohol. They mentioned primary alcohols, but alcohols in general are very polar. Hence, the IMFs for alcohol is going to be so far in this class. We're going to find acids are even more polar. But as far as Unit 1 is and Unit 2 is concerned, primary alcohols are the most polar. Then aldehydes and ketones fall in between, and they're kind of the same, basically. Ethers are going to be similar to aldehydes and ketones, a little less polar. And then, of course, the alkanes are down here and alkenes also. Now, because the oxygen is present in the carbonyl group with both aldehydes and ketones, and being moderately polar, they have a tendency to be soluble in water. Not a lot, but because of this very strong hydrogen bond in water, it can bond to the, and don't forget those little squiggly things, or it means partial, not a full charge. Okay, this is just a chart showing that alcohols, as far as the molecular weight goes, and as far as IMFs go. So again, the stronger the IMF, higher the boiling point, higher melting point, high surface tension. Now, one of the reactions we studied, excuse me, in the last unit was oxidation of alcohols. Primary alcohols immediately oxidize to the aldehyde. And then that aldehyde is further oxidized to the acid. So as far as this unit goes, you have to name the aldehydes and ketones, where before you just had to write aldehyde or ketone. Secondary alcohols produce a ketone, and then because there's no H here on this carbon, there's an H here, hence it can be oxidized. Two H's on the aldehyde or the primary alcohol, so it can be oxidized twice. The aldehyde has an H there that can be oxidized, and the ketone has no H there, so it can no longer be oxidized. And of course, we have tertiary alcohols that have 0 hydrogens, hence there's no reaction. Okay, this reactivity regarding oxidation is why they put aldehydes and ketones in separate kind of reaction categories. They call them, this slide calls it a family. Aldehydes are easily oxidized and because we have an oxygen atmosphere, when you buy an aldehyde at the, when the stockroom buys aldehydes for its shelves, they have a short lifespan because they easily are oxidized. Hence, they're more expensive, unfortunately, because the big warehouse at which we buy stuff also has to have a shelf life that's short because they easily oxidize, hence they're more expensive. Okay, so let me clear this here. Okay, so what we have here is a test tube with acetone in it, a ketone. And we have benzaldehyde, which is an aldehyde. This is the oxidizing agent. When we pour, and if it changes, in other words, if it oxidizes something, its color will change from this orange to something else. And it depends on the oxidizing agent you're using. In this case, it's potassium dichromate. Potassium dichromate goes to this kind of bluish gray when it's oxidized. So when this goes in there, it produces these guys. So the fact there was no color change here means that there was nothing that could be oxidized. So that means that has to be the ketone. Here, there was a color change. Hence, something was oxidized. That's why that's the aldehyde. Now we're going to be doing tests like this in wet labs. In fact, the test next week, not the test, the lab next week is on alcohols, and you're going to be oxidizing and reducing alcohols in that lab. So we'll be doing something similar to this. Now we're going to be learning about the Tollens test and the Benedict's test a lot. You're going to need to know those reactions, and I'll be going over those in detail. But those are the main reactions used in both carbohydrates, aldehydes, ketones, and alcohols. Okay, so let me clear this up. And you definitely will need to know this reaction, because we'll be using this reaction for both carbs and aldehydes and ketones. Okay, Tollens test involves this silver cation, Ag+. And what happens is Ag+ is easily oxidized, easily reduced to silver if there's something that can be oxidized. So the aldehyde is what's being oxidized. So the aldehyde goes to the acid salt because it's in an alkaline environment. Hence, there's no H on the end of that O there. So that's being oxidized. The silver is being reduced. And remember, oxidation reduction has to happen simultaneously because you're either losing or gaining an H or losing and gaining an electron. So you have to have a donor and a recipient. So in the case of aldehydes, we're losing an H. In the case of the silver +1, we're gaining an electron. Hence, this is going to be silver metal. So for this reaction, you don't need to know that. You need to know this instead. And that means you don't have to worry about that. That's just a spectator ion. And this happens to be balanced, but you don't have to balance it because organic chemistry, we don't balance reactions. I don't know why it's balanced here, but anyway. Okay, so that's the Tollens reagent, and you definitely need to know this. And a very similar reaction is using, it's called Benedict's reagent, which is basically copper +2 ion. Excuse me. And it also is an oxidation reduction reaction. So the copper +2 goes to +1. So the +2 is reduced to +1. So that is reduction. The aldehydes go again to the carboxylic ion or salt. And this is again as an alkaline or basic solution. But these two only differ with what's being oxidized. In case of Tollens, it's silver. In case of Benedict's, it's copper. So if we look down here, and in the case of Benedict's solution, there's one exception. Remember I said ketones gives no reaction, except with these three cases. If you've got two carbonyls side by side here, or if you've got a carbonyl and an alcohol side by side, you'll get a positive reaction with Benedict's, even though, of course, this is an aldehyde. But this is a ketone. That's a ketone. Let me make this bigger so you can see it. Of course, this is an aldehyde, so that can be oxidized because of that hydrogen there. Okay, so because you've got this guy, so this is the ketone part over here. This is functioning as an aldehyde here. This is a ketone only. And this is a combination of alcohol and aldehyde. So these you could predict you'd get a positive reaction because of this part here. But this guy on the end here, you wouldn't predict would be able to oxidize, but it does. Now those are going to come into play when we get into carbohydrates. And we'll go over that again. Okay, so Benedict's copper, Tollen's silver, and they're both oxidized. Okay, now an aldehyde can be both oxidized and reduced. If we reduce the aldehyde, it goes to a primary alcohol. And there needs to be some kind of catalyst. And again, usually it's platinum, but it can be also chromium. There's a number of metals you can use for catalyst, but normally everyone just quotes platinum, but basically it's a metal catalyst. I've been really dry today. Oh. Okay. Ketones can also be reduced. They can't be oxidized, but they can be reduced in the same environment as the aldehydes. And it goes to a secondary alcohol. Now these reactions go this way. So these are both two-way reactions. So one way to make an alcohol is reducing make an alcohol. Okay, we can take an alkene. To an alcohol. We can take an aldehyde or a ketone to an alcohol. So, for example, we have propanol, 3-carbon aldehyde. In a hydrogen atmosphere, we're going to end up, when I say hydrogen atmosphere, that's like bubbling it through. We're going to end up with the primary alcohol, propanol, 1-propanol. The acetone version, 3 carbons, in a reductive environment, we're going to end up with 2-propanol or isopropyl alcohol or rubbing alcohol. Okay, those are the simplest reactions for aldehydes and ketones. So let's do some examples before I go on. Let's say, let me grab a flow chart. I don't see one on here. I see one. Let me do everything now. And let me clean this up. Okay, so above that squiggly line is basically unit 1, unit 2 is basically below the line. Now, all these arrows, we can go basically go the opposite way in all these. All these are being reduced. Now, the tricky part on this unit is these reactions down here. The orange ones. We're going to be making something called a hemiacetal and an acetal and a hemiketal and a ketal. So, and those are a little trickier to understand. So let's do some examples of okay, say I have that alcohol, primary alcohol, and I decide to oxidize it. Okay, so you need to identify the fact that it's a primary alcohol and not a secondary or tertiary alcohol. Because you're going to get different products depending on what class of alcohol it is. In the case of a primary alcohol, when we oxidize it, we're going to end up with the same backbone. So we have 1, 2, 3, 4. 1, 2, 3, 4. Only the OH is going to be oxidized to that, the aldehyde. So the number of carbons in the backbone is the same. Now, when we get to those ketals and acetals, it's really important to identify the backbone because in those reactions, we're going to have two backbones. And then aldehydes, if you remember from unit 1, can be further oxidized to the acid. And then, of course, you always have to name them. So this is a 4-carbon alcohol, so it's going to be a 1-butanol. And this is going to be a, now I'm going to do something that isn't necessary. 1-butanol. And what's not necessary is to say 1-butanol. Why can I just say butanol? Why is butanol by itself without the 1 okay?
Because for butanol, it's always on 1.
Exactly. It's always on 1, so why put the 1 in there? You may put the 1 in there if you'd like, so that it's consistent. In textbooks, you're not going to see the 1 there, because it has to be there. Now, the exception, unfortunately, is if you have, say you have this. Well, how are you going to name that? Well, you got to name it as 1, 2, 3, 4. And so it's going to be a 1,4-butadiol. So here you got to put the 1 in. So if you put the 1 on the 1,4, I want to put it on just the 1. That's why I tell students putting the 1 with an aldehyde name is fine, because it's that way it's consistent. Okay. And then, of course, one of the problems making aldehydes is that the reaction doesn't stop at aldehydes. It continues on to the acid. So you have to be careful what you oxidize the alcohol with to get your aldehyde to stop there. Normally, people use a mild oxidizing reagent to bring it to the aldehyde. You still get some acid, but not as much. If you use a strong oxidizing agent, it goes bam, 100% acid, no aldehydes at all. So it just depends on what oxidizing agent you're using to create your aldehyde. Okay, so that would be a typical reaction. We've named the products. We've named the condition, which is O for oxidizing. In different textbooks, they'll actually tell you the oxidizing agent. They'll say like potassium dichromate and all that stuff. In here, I just want you to know it's oxidized. Okay, so does that make sense? This is kind of like Unit 1 stuff. I'll say we had our butanol. And we decided to reduce it. Okay, reducing means we add hydrogens back in, and the hydrogen would be added to the oxygen on the end. And again, we're going to have same backbone. All right, so let's do another kind of reaction. Let's do a synthesis problem. How would you make that? Well, first of all, what is it? Well, if we named it, is it an aldehyde or ketone, first of all?
It's aldehyde.
Then ketone. Remember, aldehydes cannot be in rings because they have to be on the end. And in a cyclic compound, there is no end to the backbone. This is the backbone here. So it's a ketone. And how do you make ketones? Now, this is a unit 1 question. How do you make a ketone?
You
You
oxidize it?
oxi-
I'm sorry? I think I heard oxidation. Is that what I heard?
from secondary alcohol. Oxidation of secondary alcohol.
Exactly. Oxidation of secondary alcohol. So we have to have the same backbone, which is going to be the 6-sided ring. And that's where the secondary alcohol is going to be. So this is going to be cyclohexanol. This is going to be cyclohexanone. Right. So you have to identify, and then you can use your flow chart. How do we make the ketone? We just go backwards over to here. So we are oxidizing a secondary alcohol. That's my dog underneath my chair here. He's pretty old. So he has his moments when he kind of like dry cough. That almost sounds like he's gonna barf up something, but he never does. Okay, so that was very good. I don't know who mentioned that, but very good. Okay, so let's do another one here. Let's make that. Okay, first of all, what is it? Is it an alcohol, ketone, aldehyde, alkene, alkane? Identify it. Boom. Okay, it's an aldehyde. So, how do you make aldehydes? Well, one way to make them is using a oxidizing agent on a primary alcohol. Let's a methyl group there. Okay, so let's name this guy here. Okay, 1, 2, 3, 4, 5. And it's an aldehyde, so it's a pentanal with a branch at a methyl branch at carbon 3. So that's 3-methyl pentanal. Okay, and we're going to keep the backbone. And we're going to start with a primary 5-carbon alcohol. With a branch at 3. So this is going to be 3-methyl pentanol in an oxidative environment. Now I use highlighter for backbones all the time. And Monday's class, when they taking their test, about half the class did it as well. So I would, if it helps, use a highlighter. Only problem is you can't erase a highlighter unless you're on a tablet or something like that, like I'm doing. Okay, so let's do one more reaction here. Let's do a let's do a Benedict's reaction with an aldehyde. Let's take simple aldehyde, propanal. And if you remember now, Benedict's solution has got the copper in it. So I'm going to add copper. And I'm going to add a basic solution. And then what do we get? So if this is truly propanal, it'll be oxidized to the same backbone. And we're going to end up with the acid salt. And the copper is going to go to copper 1. And that is a reductive process. Now, if you remember from 305, the oxidation number of copper plus 2 is 2. Oxidation number for copper plus 1 is 1. So the oxidation number goes from 2 to 1. That's why it's called reduction. You don't need to know that. You just need to know that we're reducing the charge by 1. Okay, and one last thing. We want to maintain our carbon backbone. Now there's some spectator ions there that I did not include, nor did I balance this thing. The main thing is I want you to know that there's an oxidation reduction going on, and it's a very, very important test for aldehydes and ketones. Now, if this was acetone, the ketone version, you would get no change. Now, this is a blue color, a copper plus 2. And this is a orange color. So when the blue goes to orange, you know that something has happened. And because we are using a Benedict's solution, which is a basic solution containing usually copper nitrate or something like that, we end up making, and this, the reason why this is orange, we make this oxide, copper oxide, and that copper oxide is what is the orange color. And again, you need to know this. Okay, now, what I'm going to do now is what happens when you add, and I'm going to go into extreme detail in this. What happens when you add an aldehyde and an alcohol together? This is a series of reactions you get. Any aldehyde, oops. Any aldehyde plus an alcohol will form first a hemiacetal, and then it'll continue on to the full acetal. Okay, there's also a ketone version of this that's called a ketal. Okay, so this is the original backbone. And that purple is the secondary backbone. So let's see. So okay, so the primary backbone comes from the original aldehyde. The secondary backbones come from the added alcohols. So you can go backwards and forwards on this series. And the tricky part is identifying what the secondary and primary backbones are, so you can trace it back to what you start with. Okay. So let's do an example now. Let me take these little. Okay. Aldehyde is primary. In a minute, we're going to do starting with the ketone, and that would be primary. So whatever the backbone is of your aldehyde is going to be maintained. The alcohol is going to come off of this special carbon. So the name of the game in this is everything centers around the anomeric carbon. That's where the alcohols are added to. So this alcohol is going to add the anomeric carbon. This alcohol here is going to add the anomeric carbon. And here, so I'm going to put a red dot by the anomeric carbon. And everything's going to attach to it or come off of it. See, these are double forwards and backwards reactions. So here's the alcohol. Here's the hemiacetal. And we have the anomeric carbon there in the middle still. Now we're going to find this anomeric carbon concept in carbohydrates as well. And that's going to be where carbohydrates are cyclic, except when they're not cyclic, and that's when they open up. And the reason why they're cyclic is because it's more stable than when they're open. And we're going to find that that's where the reactions happen in carbohydrates, is this reaction here. So this is a very fundamental reaction in carbohydrates. And the problem with carbohydrates are the structures are more complicated than this. But you've got an anomeric carbon in all carbohydrates. You've got, when the carbohydrate opens up, it forms an aldehyde and an alcohol. And then when they close back up, they form a hemiacetal. So it goes back and forth from open, closed, open, closed, open, closed. And when they're open, they expose an aldehyde, and aldehydes are very reactive. So if we are in an oxidative environment like with Benedict's solution, that sugar that is opened up is going to be reacted. So that carbon +2 will go to carbon +1 if it's Benedict's. Bottom line is, this is a crucial reaction in carbohydrates. So I can't emphasize this enough to understand this reaction going back and forth. Now, how do you know if you've got a hemiacetal or acetal or nothing? Okay, I have a little device I made up. It's a 3-step process. Okay, notice we have in both an acetal and a hemiacetal, we have the OCO, OCO. If it's yes, then you have something. You have either a hemiacetal, an acetal, or a hemiketal, or a ketal. So which is it? Step number 2 is on the anomeric carbon. Is an H present? If an H is present, then you have either a okay. On the anomeric carbon again is OH present. If OH is present, you have a hemi something. Let's be more specific. So you have a hemiacetal or hemiketal. Okay, so let's. Oh, a squirrel just ran by my window. Okay. Now we're going to do a lot of these examples, working with acetals and ketals and all that stuff. But you have to be able to identify it. You have to be able to identify it first before you can make it. Okay, so if we have oh, I don't know. Okay, we got this thing here. Identify it. By the way, we're not going to be naming acetals and ketals and hemiacetals and hemiketals, except in the case of carbs, which will be identified with a common sugar. Okay, well, first of all, number one, OCO, is that present? Yes, we have. Let me do this in blue. We have OCO. Okay, as soon as we have OCO, that means we have an anomeric carbon. So that's going to be the anomeric carbon right there. Okay, so that means we have a ketal, acetal, hemiacetal, hemiketal. Which one is it? Okay, number two, is H present with the anomeric carbon? Yes. H right there in this carbon. Yeah, one of the acetals, hemi or full acetal. Okay, so we know it's either an hemiacetal or an acetal. Okay, number three, is an OH present? Yes, so that means it's a hemiacetal. So here's the OH. So it's going to be yes, yes, yes. So that means it is ketal, acetal, etc. This means it's some kind of acetal. And this means it's a hemiacetal. So number one, is OCO present? In other words, we have two oxygens attached to one carbon. Excuse me. If so, then it's something. Either one of the four. Hemiketal, hemiacetal, hemi or full-blown acetal or full-blown ketal. Okay, so we've got the H there. Yes, that means it's some kind of acetal, either hemi or full-blown. And we have an OH, that means it's a hemiacetal. Okay. So there's a bunch of stuff we've done here. And what I'm going to do is end here. I'm going to do another couple examples. I'm going to end here at this point. And actually, I'm going to cover the ketone version as opposed to the aldehyde version. In fact, let me do that right now, and then we'll come back to this. Let's see, where is it? Where's the ketone? Here's the ketone. Okay. All right, so we have the alcohol again, and then we have the ketone. And the ketone is the primary backbone. That'll be carried throughout the whole thing. The alcohol is the secondary backbone, and that'll be carried out attaching to the anomeric carbon. And I'm going to put a red dot by the anomeric carbon. Now notice this uses R and R prime. What they're saying there, it's the R prime is different than the R. It's something else. Sometimes they have double prime also. Yep, R prime, R double prime. Okay. So let's look at an example now. So again, the alcohols are going to be using my test here. So let's look at this example here. And let's determine what it is. Okay, so number one, we have OCO. So that's a yes. Okay, number two is H present. No. And it's some kind of ketal, not an acetal or hemiacetal. Is OH present? No. And it's not a hemi. That means it is a ketal. So this test, I've never seen in any book. And so I said, we need a flow chart, and that's what this is, a flow chart. And so I used to teach computer programming, so I'm into flow charts. So anyway, so it's a ketal. I mean, in fact, it even says so there. Okay, and this is the anomeric carbon right here. Okay, let's do this guy here. Okay, we have OCO. Is H present? No. That means it's a ketal or hemiketal. Number three is OH present, yes. That means it's a hemiketal. Now, the ketal means it comes from a ketone. Acetal means it comes from an aldehyde, okay? All right, so I'm going to do a couple more examples here of identifying, and then we are going to end this. Okay, so let's say we have all right, what is this? Is this a ketal, hemiketal, hemiacetal, or an acetal? Well, does it answer the first one? Is there an OCO there? No. There's not a carbon there with two oxygens attached to it. So this is not ketal, acetal, or hemi versions. So there is no anomeric carbon. So the crucial step is number one. Do we have an OCO? And that means we've identified an anomeric carbon. Okay. Are there any questions about how to go through these 3 steps? Okay. Yeah, Logan, this is definitely new stuff. This one is definitely not on test 1. Oh, the lab manuals are in. Let's see, are we over a new topic today? Yes. Are we going to have a periodic table for the exam? No, but you're gonna have a flow chart for the exam. Who is this? Galena. Do you want a periodic table?
Yeah, I would like one.
Okay. Let's see, I should have a stack of them here in my office. And I do. I'll bring one in for you.
Thank you.
Anyone else who wants one? The problem is there's a class before us that sometimes goes to quarter till. I will be there as soon as I can. I'm gonna start this. I need to stop the recording here.